Chat students, we are getting into the next lesson of this this chapter 3 with the correlation and scatter plots and such. So let's go ahead and get back into it. All right, so we left off talking about this correlation coefficient, which we call R, and we were describing how it tells us how strong a relationship is. There's more that we're going to be looking at with that, obviously. But the first thing I want to do is I want to go ahead and look at some examples of different R values that we're going to end up seeing as we go through this unit, and how you can sort of predict what the R value will look like just by looking at this graph. So let's start with like what the strongest relationship would be. So look at this, R is negative 0.99. That's almost a perfect linear relationship, and look how tightly formatted these points are. They're really close together and they make that nice negative linear form, okay? But you can see them, and this one here, 0.9 for this one, which is pretty close together. It's not near as tight as this far bottom right one, but it definitely has that strong linear relationship. And then this one here, you can see the different levels of how we're finding these linear trends as the data goes like either positive linear or negative linear. And then of course you see one that doesn't have any relationship at all, no linear relationship, which is this one here, okay? There doesn't seem to be a linear correlation, okay? So just to talk about what your calculator is actually doing when you're doing a correlation, move on to the next slide to show this. So here is the formula, which does not look very good, right? As you can see here, it's sort of like the z-scores of each one of these. It's almost its own standard deviation, but we've talked about z-score before. Well, actually, no, it's not necessarily like, yeah, it is kind of like a z-score actually. It's the positional value of the X list over its standard deviation, so that's like a z-score for that, times the y value z-score that correlates to that, that's paired up. You keep doing that for every pair and add them all together, and then you divide by 1 over n minus 1, which is degrees of freedom. So this is very similar to a standard deviation type formula, but it's what's measuring that strength of the linear relationship, okay? So it's describing on here what our calculator's doing, and thank goodness, right? Having to do this by hand would be pretty brutal, okay? But that's the idea. And so any values that are extreme are going to throw this formula off. It's going to make this a lot larger, and it's going to change our value from being closer to 1 or negative 1, making that strong trend. Okay, so if the values don't have a relationship, it actually becomes closer to 0. Pretty amazing to think. I always like looking at these, just how they came up with this stuff. But if you think about all that we've looked at this year, we've talked about like how to create standard deviation. That's really all this is. It's like the z-score of this one, of the X, z-score of the Y, and you put it over the number. So it's almost like the average of the average. You don't have to think about it too much. Let's just go ahead and talk about facts of correlation. Now you are going to need to write some of this down. Go ahead and put facts about correlation, because these are going to be important. So correlation how it behaves is more important than the details of the formula. Yeah, that's why we're not going to harp on this formula too much. So what can happen with R, okay? So correlation makes no distinction between explanatory and response variables, okay? It doesn't know that Alabama had won the games with the points. It doesn't really care. It's just taking their numeric values, okay? R does not change when we change the units of measurement of X or both, X, Y, or both, okay? Should scale appropriately. It's getting rid of any of that detail about measurement, and is just comparing all the numbers together. So it's a cumulative thing of all the data. So if I shift all the measurements of X or transform it, it shouldn't really matter. Next, correlation R itself has no unit of measurement. That's very similar to standard deviation. There's no measurement for standard deviation, okay? And then we have some cautions down here. You have to have quantitative variables to do this. They have to be, you can't have a yes or no question or type variable to do this. Correlation does not describe curved relationships between variables, no matter how strong the relationship is. Correlation is not resistant. Remember, outliers affect it greatly, and we saw that in the last lesson. And then it's not a complete summary of two variable data. Okay? Not a complete summary. So a lot of information on this slide, but it is important that we have that available. Questions 24 and 25, that's where you're going to use a lot of this concepts for this. I will have the Delta Math up very soon so that you can start working through it. But let's go ahead and pause and let you write this. All right, so this is saying estimate the correlation. For me, this is like a 0 here. But we're going to go ahead and look at a little example. Let's do this one here. Yes. Okay, so we're going to talk a little bit more about correlation. And here we see something that's very similar to what we had in our slides, but we're going to talk about ice cream sales, okay? Do you think there is a correlation between ice cream sales and temperature, right? That's what we want to know. So the local ice cream shop keeps track of how much ice cream they sell versus the temperature on that day. Here are the figures for the last 12 days. Now this is in Celsius, so obviously this isn't America, right? But let's go ahead and make a spreadsheet, and let's type in this data. So we're gonna call this X and this Y, and then I'm gonna go ahead and oh, I need to move my camera. I guess you can type this. You will need to go ahead and grab your Inspire, and we'll start. I'll just type this in with you. 215, 325. And if you need to pause the video, go ahead and do that. I won't be pausing it though. You can take your time typing in all these values. So there's my 12 sales amount. So X is sales. So, and that's interesting. We've talked about the X, or this left value. Does that explain the ice cream sales? So this is an interesting situation where it really feels like this list should be X and this one should be Y. So I'm actually going to change that. I'm going to delete this, call this Y. Oh, come on now. I guess it's too late to do that. I'm just going to call this IC now for ice cream, and this one will be temp, just to make that. I would rather think that because it makes more sense that the temperature would explain the sales, right? If we think about it, hotter days should increase the sales. So I am going to change that because we still need to be having that in our mindset. Okay, explanatory variable needs to be the X. So let's put all the temperatures in. One at a time here. There it is. Okay, so I've got all mine in. Again, if you need to pause me real quick, go ahead and do that. Make sure you've got yours typed into your Inspire. All right, so we are going to make a scatter plot of this. So we're gonna, again, hopefully you've paused me to put in all your data, but go ahead and add a page, Control Doc. Data and statistics is what we want. We're gonna make this our temperature. We said it makes sense for that explanatory variable X to be temperature. It seems like that's what is going to give us the response of sales, right? So this one up here would be ice cream. And what we see here is exactly what we thought, right? Higher temperatures yielded more ice cream sales. So let's do this. Let's flip these. Let's put ice cream as the X, like the sales. And you'll notice that it still has that positive trend, okay? But temperature is going to be better suited to be that X variable. So it's just going to invert it if we do that. So let's go ahead and get our R value. Let's see how strong. And you can kind of predict right now, if we're thinking about where it would be, it's definitely positive, and it feels like it's going to be pretty strong. I would say greater than 0.9. It's going to be really close to 1 looking at it. So let's go ahead and go back here, go over to the blank column. So we're on the first tab, menu, statistics, stat calculations. We want number 4 here, linear regression. X list is going to be temperature, Y list, ice cream sales, hit OK. That R value, yeah, 0.96 is very strong, positive linear relationship that we have there, okay? And that's what we wanted to know. All right, really good. Really good. So we've got that, again, sort of a review there. So I have an example here that I want to talk about. We see, look at this one. It says sunglasses versus ice cream, okay? So our ice cream shop finds how many sunglasses were sold by a big store each day and compares to their ice cream sales. And look at this, we have a nice positive linear trend. I would say this would be a very high correlation coefficient as well, that R value would be close to 1. Should feel stranger, right? Because does sunglasses explain ice cream? No, it doesn't, right? They're not correlated in any way, right? They're not necessarily correlated in any way, and that's what we say. There's a famous saying in statistics, and you may have heard it before. Correlation does not imply causation, right? So just because there is a correlation here, because there is a correlation, they do have a positive trend. That doesn't mean that selling sunglasses is causing the ice cream sales to go up. Here, when we look at our graph, the temperature, is that causing the ice cream sales to go up? Well, it does make sense, right? There almost seems to be this causal relationship there. But in this example here, we're seeing that just because there's correlation does not mean that one is causing the other. And that's a very important rule to learn, okay? Correlation makes no distinction between explanatory and response variable, okay? So that's something to keep in mind, is that this R value, just because it's a very strong relationship, doesn't mean that it's not like the end all be all, right? It just means that there is a strong linear relationship, and that's really it. Okay, that's what this is for. Okay, so we're going to move on to the next couple of topics, which is we are going to do what's called least squares regression. That's what we want to talk about right now. Okay, so a least squares regression, we are going to be making what's called the line of best fit. So in your notes, draw a line and write down this definition here. Linear regression line is a line that describes how a response variable y changes as the explanatory variable x changes. We're actually going to write this entire definition here because we often use a regression line to predict the value of y for a given x. Okay, that's what we're going to do. So I'm going to pause and let you write that. Okay, so to create it on your calculator, you're going to press, you have to be on the scatter plot. Press menu. So let's go to our scatter plot here. So everybody should be on this menu. Then you're going to click analyze. Then you're going to see pretty quickly regression. And we have to show which one we want. There's a lot of different types. Analyze, regression. And what we want is the linear A plus BX is what we are going to want to use. So it's right here. So we click that and look at that. We get a line. So make sure that you've got that on your in your notes on how to make that. I would feel very confident that you've made one of these before. So this shouldn't be anything too new. But in a lot of examples in the problem set, you're having to use these ideas. Okay, for instance, let me go to the left display here. This is number 28. It's saying what is the intercept of the least squares regression line? Here's this line, right? So we'll talk about that one, and then it's talking about predict what would happen with 10 grams of carbon emission. And then we'll talk about this open circle as well, and talk about residuals. We still got several things to talk about, 31, 32, different things in there. So we'll discuss those as they come up. But for now, we've got our definition for a regression line and how to find them if we need it, okay? So interpreting a regression line, it's a model for the data, sort of like how density curves, like a normal curve, models the data. It gives us a mathematical descriptor about the relationship between y and x, okay? So we have the regression line. Here's going to be our equation, okay? I would actually like you to write that down. And then we've got these after you write this down, let me highlight it just so y'all have it. That's the line equation, and we have these bullet points. So in this equation, we'll put these bullet points, okay? So you read that as y hat, right? We're familiar with p hat, right? It's the predicted value of the response variable y for a given value of x. So just like you learned back in middle school, the value, the coefficient to that x is your slope, okay? Change in y over the change in x, and that's so it's the unit rate, right? And then a is the y-intercept, which is the predicted value when x is equal to 0. Okay, so if we go, actually I'll pause and let you write that. Alrighty. So if we go here, what is this predicted value down here? Now our scale's a little bit off, but we can see our y-intercept is negative at 0 degrees Fahrenheit, Earth Celsius, which is freezing, by the way. This says negative money, so the negative cells, which isn't really possible. A lot of times the y-intercepts don't make a ton of sense in some of these regression formulas, but this should be our best predictor on realistic temperatures. But we don't really expect them to sell ice cream in freezing temperatures, although I'm sure some of you have had ice cream, in the winter, which is fine. But as far as like being a business, it's not typically going to go too well. Okay. There's that. So let's talk about this example over here on the left. Consider the following scatter plot for amounts of carbon monoxide and nitrogen oxide in grams per mile driven in the exhaust of cars. Here's the least squares regression. So, and they make a comparison. There seems to be a negative trend to this data. The more carbon that you're outputting, the less nitrogen oxide that you're emitting, okay? And vice versa, okay? The more of this, the less of the carbon. I don't really know the chemistry behind any of these or which one's better or worse, so maybe y'all do. But if we talk about the intercept, so really if we extend this line, where is it going to cross? That's what we want to know. And really the only one that makes sense is C. We know it's not going to go past 2. So really that's all this is talking about. Where is the intercept, okay? And then we can't really, let's see, can we answer 29? Okay, yeah, what would happen? So this is what we're going to get to soon using predictors. So I'm not going to go over 29 yet. Let's go down here. In a statistics course, a linear regression equation is computed to predict the final exam score from the score on the first test. The equation of the least squares regression line is 10 plus 0.9x, where y hat represents the predicted final exam score and x is the score on the first exam. So the first test score is, what is that? Okay, this is just going back. This is not intercept or slope, right? It's not neither of these, so you may be thinking, oh, that's what that is. But we're saying x is the score on the first exam. So x is our explanatory variable. So I was hoping for more than that. I guess I'm going to have to do some more teaching before I talk about these. So we'll probably answer number 29 and 30 in a second. We'll answer 29 in a second. So, all right. So a problem here, interpreting slope and Y-intercept. Okay. No, I don't like that one. Let's talk about prediction. Okay. We're gonna do another example. How much time do I have? 20 minutes. Okay, I think I can do this. All right. Okay, let's do this one here. It says the following data shows the number of miles driven and advertised for 11 used Honda CR-Vs from 2002 to 2006. Scatter plot below shows a strong negative linear association between miles driven and advertised cost. The correlation is negative 8.74. The line on the plot is the regression line for predicting advertised price based on the number of miles. The regression line, it gives us our regression line here, where Y is the predicted cost and X is the number of miles in the thousands. Will the circled point, all right, we don't know what a residual is yet, but we'll get that in a second. Need that either. So this example is not really doing what I want it to, so sorry about that. We're going to talk about predicting values, okay? And that's what we're going to do here. We'll still use this example. Fine. We have this here. So I actually drive a CR-V. I don't know if anybody knew that. I drive a 2003 Honda CR-V. So that's the one that I have, except it's like maroon. It's this one here. That's the one I drive. It's definitely probably not worth too much. I bought it for like $7,000. It actually had, I think I've been on this display here. We're talking about this. Here's the chart. It actually had 88,000 miles when I bought it it was like $7,000. 2017, 28, yeah, 2017, yeah, it was 2017. So that's really pretty good. It only had one driver. But since then I've put on a lot of miles. I would say I'm probably at 125,000. So we can use this to help me predict what it would cost, right? So let's do a prediction here. And I'm gonna edit this. Go ahead and do this for me. Write down this, so Honda CR-Vs, 2002 to 2006 model years, okay? And you can put this right here. Y hat is predicted cost, X is number of miles, and then you can also write this formula down in your notes, okay? What is the value of Mr. Woods' 2003 Honda CR-V? By the way, this is not calculated at all. I didn't even know about this example until I opened up this worksheet, so it's pretty funny. Honda CR-V with 125,000 miles. We'll see if this does a pretty good job predicting that. So I'm going to we're going to type in our formula here. So let me just use this little scratch pad calculator. So it's 18773 minus 86.18 times, and let's put 125,000 miles in there. And that's what these formulas can be used for, is making these predictions. Following this trend, this pattern, can make this prediction. What did I do wrong here? It can't be worth negative dollars. 25,000. Oh, they're going up by thousands of miles. So yeah, okay, that makes sense. We need to put 125 here. There we go. 8,000. That's probably what a dealer could get for it. I could not sell it for that much. I know that. It's not in bad shape, but $8,000? No, I don't think I could get that much for it. And I might have more miles than I think on there. But this is at least supposed to get us in a ballpark area for what it could be. So that's how we can use these. So if we wanted to figure out, okay, what would be the temperature? Here's our formula here. We get in our inspires, they give us the formula here. If we wanted to see what it'd be like for a 30-degree day, like a really hot Celsius, high temperature Celsius, we could try to predict that, right? So with these predictions, we can look at 29 now. Let me get my left screen here. Looking at 29. Okay. See, the least squares regression line would predict a car that emits 10 grams of carbon or CO mile driven would emit approximately how many grams of NOx. So if we go to 10 here, here's 10, we go up and then we go over, and we can see, okay, it should be in this range here. So we're talking, so up and to the left, that looks like 1.1, right? So this, wait, right here. Looks like D would be the best choice for that one, just based on that. So this line, on this line is what can tell us what our value should be. And I could do the opposite for, if I started on this side and went the other way, I could find that point, okay, that predictor, where it should be. Okay, so 10 here, over. Okay, so that's how we can use it to do predictions, and if they don't put it in here, then I'm going to put it. It has a special name. Yeah. So we don't really call it, it is a prediction, but it has a special name. You have what's called extrapolation. So you may have heard somebody say, how did you extrapolate that from what I said? You've heard that a lot. And extrapolate means you're going outside of the boundaries of the line. And I realize I haven't changed my display here. So extrapolate is extrapolation is the use of the regression line for a prediction far outside the interval of values of X used to obtain the lines. Predictions are not often accurate. Okay. And then you have what's called interpolation. Which I guess they didn't have in here, but I do want to write this down. Prediction, and we'll just write it this way. Prediction inside the interval of values for the exponential variable X. That's what we just did on number 29. That was an interpolation, because that was within the range of X values, right? The line, there were values above and below it, so that was an interpolation, which is a little bit better at making predictions. It's still off a little bit, but it still helps us a lot with that. So extrapolation, interpolation, there will be some questions on the problem set where you have to do that. Number 43. Yeah. 56, 43, and just the different ones that are on there. Alrighty. Anyway, I think I needed to pause. I don't know if I did. I'm pausing. Okay, next we're going to talk about residuals, and this will probably be our last topic today. We're going to talk about residuals. So in most cases, no line will pass exactly through all the points in a scatter plot. That's almost always guaranteed. Like none of these lines here from our example, or there's just a few points. So this one here is probably the best one. Look at that, it kind of got cut straight through it. But that's very rare, okay? A good regression line makes the vertical distances of the line, of the points from the line, as small as possible. Okay, that's why we have that difference of X and X bar, Y and Y bar, okay? So a residual is what we describe that as. It's the difference between an observed value of the response variable and the value predicted by the regression line. Okay, so here's all of our formulas for that. So you can write all that down for me. Yeah, and they give an example of that. So I'll pause here. You can write that. So we have this written down now. We're not going to be able to get these dots or these lines like they have here, okay? We actually have something else that occurs on the Inspire. If you press Menu, Analyze, and you see this Residuals tab, number 7. Oops, I didn't want that one. When you go to that, you will see Residual Plot and then Residual Squares, which next lesson we'll talk about residual squares, but we need to do residual plots. So go ahead and click that. you see here is the distances. We take this line, the diagonal line, the positive sloped line, and we flatten it out and call it 0. And then all these points show their distance from that residual line. Okay, so it doesn't have like these lines here, but you could imagine we could draw those lines vertically to it, and that's what a residual is, and that's how we can look at the residual plot. It's showing us how close that line, how well of a job it does at fitting the data, because the goal, a good regression line makes the vertical distance as small as possible. So this is the smallest residuals that could be created by a line. That's why it's called the line of best fit. Okay, this was the best fit that we could get. Okay, so let's talk a little bit more about the residuals. Let me go back to that example that had a residual question. Where's that at? So it was talking about that. Number 30 is what I want to talk about with residual, and then we'll end it there. But let's go to the left camera again. So it says we're using this graph here. It says in the scatter plot, the point indicated by the open circle, that's right here. You can see that. So A has a negative value for the residual, B has a positive value for the residual, 0 value for the residual, has a 0 value for the correlation, or E is an outlier. So to make sense of this, you'll notice that it's below the line, okay? And if we go back to our formula here, here's the observed Y value minus the predicted. So for this, you'll notice that the predicted Y value is going to be bigger than the observed Y value, okay? Going back to the screen, this Y value is smaller than the actual line. That's what this is talking about. So from the formula for a residual, the Y value of this minus the Y value of this is going to create a negative value. So A would be the best choice on this. Yes, you can have a negative residual. It's not a distance. Distance is positive, but this is not a distance, even though it looked like we were getting distances with these little lines. No, that's not the case. It can be a negative value. So this would have a negative value for the residual. A 0 value would only occur if it was flat on the actual line, okay? So like for instance, this one here would be pretty much a 0 residual, okay? The ones above are gonna be positive residuals, the ones below are negative residuals, okay? Not necessarily an outlier, it's kind of falling within that pattern overall of the total data. If all the rest of the data was tighter around that line, it could be an outlier, but it seems okay for this. All right, we're gonna stop there. A couple more topics to talk about in this slide. We got squared regressions, residual plots, which we kind of introduced, but we have least squares regression. So we'll get to all that in the next video. So I'm gonna go ahead and stop here.